Right, line P1, learning task 8, describe transformer loading. Oh, I hope you've done your pre-reading. If you took a look through here, there is vectors like you would not believe. There's a vector here, a vector there, another set of vectors, lots of vectors going all over the place. In fact, this whole learning task over here has gone pretty much vector crazy all over the place with lots of these different triangles that need to be explained and lots of these different associations that we have from component to component. I'm not going to go crazy with the vectors because at the end of the day, we need to be able to go and do exactly what the title says. If we go back into our ITA, once again, it says B, you must be able to describe the effects of load on a transformer, which means that we should go and examine our transformer unloaded. That's going to be the very first thing that we're going to do. And then we're going to go and examine the transformer loaded. And at the end of that, we just have to be able to go and sum it all up in a couple of sentences. What happens when we put different types of loads on there. We will go through some of the vectors, but not to the depth that you may have seen these things presented before in the past, and not to the depth that you're going to need to go and pull out some fancy trig degree or anything like that. We're just going to look at simple associations. And really the biggest association that we're always going to go and be looking at is the relationship between resistance and current. All currents that pass through resistance has to be in phase with that current, right? We've looked at, all of these power triangles before where we would go and have watts and, oh, that's terrible, 90 degree, watts, VARs, and VA. And we knew that whatever we've got for our watts, the watts are going to be true pure power. And we know that one thing about watts is that my current is in phase with the voltage. So we're just going to look for relationships between resistive components, anything that's going to be along this watts line, and currents. And then we can go line those two up. And I'm going to show you all those parallel lines inside of these vectors later on, and then we'll understand kind of what's going on inside of it. First thing that we're going to talk about, though, is an unloaded transformer. When I've got a transformer that is going to be unloaded, I have got nothing attached to this side over here. Therefore, I've got nothing that I'm going to be pulling extra out of here, which means that at the instant that I connect this, there's really just a coil of wire across here. Now, the beautiful thing is that coil is wound together into a core, and if we were to ignore everything else, we could go and say that that coil simply is an inductor over on this side, right? It's not going to anything else. It's acting just like an inductor. What does an inductor do? It creates a counter EMF to oppose the main applied EMF. We use the analogy of a little linebacker and a big linebacker, right? It's going to go and create a counter EMF, which is going to be a reflection of itself, but just a little bit smaller. It always overpowers the counter EMF, but the counter EMF pushes back against it, slows it down, and that's what slows down the rate of electrons traveling from the source through this. The instant that we go and apply it, we get the counter EMF that is going to be in the opposite direction. We do have a couple of vectors that are going to go and apply this. Let's start with our applied value of voltage. Our applied value of voltage is going to be pushed off there in whichever direction we decide that we need to go and have. It doesn't matter whether we draw it left, right, or right, left. For the sake of this learning task, they've started by drawing this thing over towards the right. All that we know is that our counter EMF is going to have to be in the opposite direction. So I'm going to go and have a counter EMF. I'm going to erase this arrowhead right now because we don't need that section yet. That counter EMF is going to be equal and opposed. In other words, if this is going to be 120 volts, then this is going to be negative 120 volts. It's my counter EMF that I'm going to have. You remember that? The formula for this, by the way, E is equal to negative L delta I. Oh, that's a terrible delta. Delta I over top of delta T that we were going to have. That's what we're getting. We're always getting an opposing value of voltage. When this is positive, this would be negative. When this would go negative, this would have to go positive. Our primary counter EMF is going to be in the same direction as my secondary induced value of voltage. So my secondary induced value of voltage is going to be drawn from the origin in the same direction. Now it's going to be, in this case, they're showing us on the transformer here that it's going to be half the volts, right? Because we've got half the turns, 100 turns, 50 turns. We get half the volts, therefore, are out of this one because of the half the turns. So I'm going to go and have this one that's just going to be superimposed over top of here. The last thing that we're going to go and talk about is just where my current itself is actually going to go and be. The current is all going to be based off of the fact that right now when it is unloaded, it is acting as an inductor. What do we know about an inductor? Well, we know Eli, that the current is going to go and lag the voltage by 90 degrees inside of a pure inductor. This is obviously not going to be completely a pure inductor. It's going to be a little bit off kilter, but right now we're drawing it theoretically where we see that we've got our applied voltage and my current that is lagging at 90 degrees. So we've got this little triangle over here that we have created out of that. They do show as well the magnetic flux inside of here. I'm not too worried about taking a look at the magnetic flux off of this one. We're more concerned with the relationship between volts and amps itself. Then they say, well, what happens when we go and apply a load to this thing? As soon as we apply a load to this thing, we now complete a path for secondary values of current. When we complete that path for our secondary values of current, we are going to go and create some lagging effects, because ultimately when we look at it, we see we've got inductance in the two transformer coils, and then we've got resistance over here. So it's going to be an RL type of circuit. Let's go back to first thing we got to ask ourselves is what drives transformers. It's always going to be the current that we're going to have on the secondary. So that's a good place for us to go and start. Now, if we take a look at the load that we had attached, we see that it is a resistive type of load, which means that anytime that I have got resistance, I'm going to go and have my current that should be in phase with the voltage. However, because we do have all the rest of those transformer components, the windings themselves, it is going to be a little bit lagged off of there. So this is where my secondary value of voltage is over here. If I did not have the inductiveness of the transformer itself, what I should have would be having a secondary current over there. But because we have got the transformer components itself, to show that in the next little bit over here, you know, these XLS that we're going to go and have, the leakage on here, as well as the actual inductance that we have on that coil. Because of that, my current moves off of the voltage and lags it a little bit. It's not lagging it much, right? If I had it lagging before, this would be a 90-degree lag if it was purely inductive, but we see that this thing is, you know, well underneath that, but it's still going to be lagging a little bit. If this is where my secondary current is, then my primary current is always going to be seen as being opposite to that. We always have, you know, whatever my primary current is and my secondary currents are going to be reflections of each other, scaled reflections of each other through a transformer. So we see that we are going to go and have my primary current over here that is going to be made up of the reflection of this, but then this gets added onto this, the magnetizing current that we originally had down there below. The first graph we looked at showed magnetizing current, then we added on the primary current and they form a new vector sum, which is going to be this one over here. That's going to be my actual primary current. The main lines that we have to really take a look at inside of here are just going to be these two currents, my secondary current here, my primary current over here, and then my voltages, my primary applied voltage, my secondary generated voltage. The rest of these are, you know, fairly inconsequential to what we're taking a look at. What happens now is as we change any sort of a value on my secondary over here, right? We're purely resistive. We see that because it does have some inherent inductive properties, even a purely resistive load on a transformer is going to be a little bit laggy, a little bit inductive. If we start to go and change this load, make it more inductive, or make it capacitive, we're going to go and change the direction that that secondary current is going to go and operate in. All right, let's go and take a look at what we have got now here through the next set of vectors. Here's one of those things that really, you know, bugs me about this stuff. They change the direction. They start out by doing all of their explanations up top here. They're showing us the applied value of voltage. They show us the applied value of voltage going in the right-hand side. They show us the counter EMF in the secondary in the opposite side. And then from this point onward, they start to go and flip that around. They put the secondary onto here and the primary onto there. In reality, what we could do if we wanted to line it up with the other is I could just draw it upside down like that. And you'll see that, look at this, it's the exact same thing as what we were just looking at over here. The applied voltage, the secondary voltage, the primary current, the secondary current that would be coming off of that one as well. They just don't go and show us that secondary value of current. This was for our unloaded transformer, so it was this diagram that they had over here. This is now going to go and be for my transformer loaded with that purely resistive load. I'm going to flip it over so it just looks familiar to what we had just gone through over here. Once again, you should be able to identify the applied, the secondary current, the primary current. And if we take a look at, all the way down over here, I'm going to go and see my applied, which is this one over here. I'm going to go and see my secondary value of voltage. Now, they start drawing this one off the angle over here because they're starting to apply a bunch of other smaller drops that are going to be inside of here, IX and LS. But most importantly, what we see is we're going to have our secondary current, and then we are going to go and have our I'm drawing that way off axis here, our primary current over here as well. All of this together is going to go and form a bunch of small power triangles inside of our transformer. Let's identify just the two main transformers that we are going to be looking at. These are my main transformers that we're going to look at. They're poorly drawn inside of a bunch of these, so even though they went vector crazy, then they got sloppy and did not draw them properly. But there's a little triangle over here, and I want you to go and imagine as if it's got a hinge. It is always going to be attached to this because I'm going to have my primary value of voltage, but I'm only going to go and get a certain amount of counter EMF because I've got some drops inside of there. Same with this side over here. There's another triangle over here. And once again, it's a 90-degree triangle, and it's going to be attached with a hinge over here, okay? You need to draw that on there. The second thing that I want you to take a look at is this triangle over here. This is my secondary. So we're really looking at the power factor of my secondary right now. For anything that is going to go and have a secondary resistive load, I'm going to go and have, well, we see that we got the X value of our triangle, which is going to be our watts. I see that the watts are in parallel with my secondary value of current. That's what that little double slash on there stands for. Just the fact that those two are going to be in parallel. What happens is that we have to always keep that little line over there in parallel with this secondary current. That's all we need to identify from this point forward. All the rest of these formulas and talk about the excitation current and things like that is good science, but it's not really needed for us to go and describe what happens to the effects of load. This is a purely resistive load that I'm seeing over here. What I'm seeing from this purely resistive load right now is that I've got a secondary value of voltage that is going to go and be somewhat small, okay? It's going to be a small value of voltage over here, but it's going to be not terribly small. It's going to be close to what we want this thing to actually go and be. When I change this to an inductive load, changing it to an inductive load is going to go and twist all of my triangles. They're the same triangles, but now what's happened is that these triangles that we had are pushing back in this direction. Remember, this is the hinge that they're attached there with. So I've taken those triangles and whoosh, pushed them in. As I do that, what happens is that my secondary value of voltage gets shorter. That's the long and short of all of those vectors that they're talking about over there, is that, look, we're going to go and get a secondary value of voltage that's going to be shorter. And the reason for that, the reason that this triangle has cammed over is because my secondary current has gone more lagging. Okay, it's an inductive load, so my secondary current has gone more lagging, and as a result, this line over here needs to parallel that, because that's talking about the resistive voltage drop inside of that transformer. So the only way that it could do that was for it to keep its attachment point over here, but to hinge backwards in that direction. If I go to a leading or to a capacitive type of load on a transformer, we get the opposite thing that's going to go and happen, right? We're going to go and have my secondary value of voltage, but now we're going to go and have a current that is going to go and be leading. So this is going to be my I secondary, and I'm going to have to go and parallel my triangle. Remember, this is my triangle over here. It's a poorly drawn 90-degree triangle that they had over there. But what I need to have happen is that this triangle here, these parallel lines have to be in parallel with these lines. Once again, for me to go and have this thing, the EG, the value of voltage that I'm placing across here stays as a constant. It's never changed from one to the next to the next. That's always stayed the same. But what's happened now is I've had to twist this triangle out in the opposite direction, like that, in order to make this line parallel with this line. And in doing so, when I twist it out, I see that my secondary value of voltage has been stretched out. It has been increased because of this capacitive load. So let's just go back to these three here really, really quickly. Once again, this is going to be a resistive load. On a resistive load, I see that my secondary voltage, that's ES. Come back here. ES and IS are in phase. And I see that this little triangle is going to go and match. It's going to be in parallel with that secondary value of current. That's for a resistive load. And so therefore, I'm going to have a certain magnitude of secondary value of voltage. This one over here, I'm going to shrink that secondary value of voltage because I've got an inductive load. The inductive load has pushed my current back down, right? It's pushed it now to make it more lagging. Because it's more lagging, I still have to go and match it. These have to be matched with these so that they're going to be parallel, which is then going to swing that triangle in and shorten up my secondary value of voltage. And the last one that we just took a look at, we had a leading current, which we had to keep the thing attached by the hinge, but we had to twist it outward in order to do that, and that stretched out our secondary value of voltage. I need you to go to the very last paragraph in this learning task and highlight that, because that's really most of this thing. Basically, it says, if we increase the power factor to a leading power factor, the transformer terminal voltage is going to go up. This is a bad thing because it means that everything that's attached to it, your house, your neighbor's house, your factory, your neighbor's factory, is all going to go and see way too much voltage out of it. So let's go and sum it all up into a couple of sentences. Just erase that there. That there. Resistive loads, inductive, and capacitive. If it's going to be a resistive load, we're just going to go and get our regular rated terminal voltage out. It's going to be normal. We're just going to call that normal voltage on the secondary. If I've got an inductive load, I'm going to go and have a reduced voltage. It shrinks it. It makes it a little bit smaller. So I'm going to have, for inductive, it's going to be reduced voltage. Okay, this is also why we want to go and do power factor correction, because as soon as I got a lagging type of load, that lagging type of load is going to drop my transformer terminal voltage. And then my capacitive is going to be an increased voltage. And all of these voltages that we're talking about are obviously not happening on the primary, but these are all going to be happening on the secondary of our transformer. Doesn't matter whether our transformer is being used as a step up or as a step down application, it is always just going to be on the secondary side. So this is the reason we do not want to go and overcorrect our power factor. If we overcorrect and go capacitive, we lift the transformer voltage. As soon as we lift the transformer voltage, then we run into problems where we burn out the transformer, we burn out equipment that's attached to it, ours, our neighbors, etc., and then we end up having to pay the bill for it. This is also the reason that we power factor correct, because otherwise we end up with too little voltage. We can end up with brownouts and things like that if we have got too lagging of a power factor. All right, that is it for what looked like it was going to be a terrible one to go and analyze. If you do have, the time, you should be reading through it all. It's good stuff that's inside there, but it's just a little bit deeper than what you need to know. For most of you, this is going to serve you through your entire career. Just knowing this, that a capacitive load lifts the voltage and it's bad, and an inductive one drops it.